So, until now we have assumed that mass transfer is not significant in terms of it is not going to increase the impedance, it is rapid, diffusion is fast, and kinetics are the rate limiting step. So, what happens when you also have mass transfer? Meaning what happens when you also have slow mass transfer? When you have diffusion playing a role or when the concentration changes, you can derive the equation for impedance while accounting for mass transfer, and normally all that's shown in the textbooks are for simple electron transfer reaction. We do not usually find expressions for impedance accounting for kinetic as well as mass transfer for any reaction which is complex, which is for example with adsorbed intermediate. Okay. And even this is fairly long derivation. So, I want to go through it, I want you to understand the implications of this. So, the reaction we take is ferrocyanide ferricyanide redox couple. Okay. So, Fe2 Fe3, but it is not just simple Fe ion, but it is surrounded by 6 cyanide groups. This pictorial here gives an idea of what we are looking at. Okay. So, I have shown the reaction as A going to be, it is reversible, I have not shown the reverse arrow here, but you can imagine A is a one entity, B is the other entity. So, it is charged Fe4 minus is A, FeCN6 3 minus is B, A can lose an electron and become B, and B can gain an electron and come as A. A and B are in solution, and in the bulk solution we assume they are completely well mixed and there is uniform concentration. Near the surface there is a formation of bound layer. On the surface the velocity of fluid is the same as velocity of the surface. So, you can consider two different scenarios, one where the bulk of the fluid is stationary, just the surface is moving and a thin layer along with the surface is dragged, that is one possibility. The other possibility, surface is stationary, fluid is moving and the fluid is considered as a bulk here, it has a completely well mixed condition, and close to the surface there is a bound layer formation and velocity on the surface is 0, velocity at the bulk is same as the bulk velocity. Typically we use what is called rotating disc electrode. So, there is an electrode where you have an electrode like a cylinder, but all the sides are surrounded by insulator, only the bottom surface is exposed, and when this is rotated fluid is pulled towards this and by centrifugal force it is pushed out or thrown out. Okay. So, it forms something like a vortex like fluid motion, but this can be approximated as a boundary layer of certain thickness. You can control the thickness of the boundary layer by changing the rotational speed. The boundary layer thickness depends on viscosity, density, etc., but if you are taking a particular fluid during operation, what is easy for us to change is the rotational speed. Okay. So, we are going to say that boundary layer has a thickness of delta. So, we can assume if we take the reference here meaning for the movement, if the electrode is taken as reference, then we will say on the electrode the velocity is 0, outside the electrode the velocity is relative to the surface it is some number. We do not even need to worry about the velocity, we just need to know the boundary layer thickness. So, we say boundary layer thickness is delta, and delta we can relate to the rotational speed and other parameters. Within the boundary layer we are going to say that the mass transfer is by diffusion alone, there is no convective mass transfer. So, we are going to assume boundary layer is stationary and mass transfer occurs from higher concentration to lower concentration. If we are generating lot of B here by going to the positive potential, then B will move away because on the surface you will get more of B generated and A will be consumed, therefore, A will come from bulk to the surface and B will go from surface to the bulk. The current here is going to be written as usual K1 multiplied by concentration of A. Previously we would have said concentration of A is a constant, now we will say concentration of A on the surface, and likewise minus K minus 1 concentration of B on the surface, and this will be different from the bulk in general. If we say that there is no stirring at all, okay, its stationary electrode, then the boundary layer thickness will go to infinity. Meaning, if the electrode is stationary, the fluid is stationary, nothing is moving, then when you convert A to B, concentration of A near the surface will keep decreasing and diffusion will happen, and there is no end to that. Practically the vessel distance from the electrode to the vessel wall will be the boundary layer thickness. In general, you can say if it is large, it is going to be considered as infinity. So, we will call that as semi infinite, because one side is electrode, it is going from 0 to infinity, it is not going from minus infinity to infinity. So, it is called as semi infinite thick boundary layer, and if you have rotation, it has a finite thickness. That is one. Second, the rate constants K10, K minus 10, they are not arbitrary in the sense they can't be varied arbitrarily, because we take the reference as the open circuit potential. At open circuit potential, current will be 0, and at open circuit potential there is no net reaction. A going to B and B going to A, they happen at the equal rate. They may happen at a fast rate or slow rate, but both will happen at the same rate. Okay. So, you would write it as K10 e power B1 e Ca at x equal to 0 minus K minus 10 e power B minus 1 e Cb at x equal to 0, and if there is no net reaction, there will not be any consumption, net consumption of A or net production of A. Therefore, there will not be any need for net diffusion from one location to another. So, everywhere concentration will be uniform. At open circuit potential, in this particular case, you will not have any net reaction, therefore, concentration will be uniform even within the boundary layer. Concentration everywhere will be same as Ca bulk and Cb bulk. Therefore, I can replace Ca at x equal to 0 with Ca bulk, Cb at x equal to 0 with Cb bulk. Potential is 0 here because it is at OCP. So, I have a relationship which says K10 and K minus 10 are related. So, if I tell this is the bulk concentration and this is K10, I can't give you K minus 10, I have already specified it. I can't give you an arbitrary number for that. So, not just in this reaction, in general when you consider all the reactions, reversible reactions, you will have to say at equilibrium the net rate is 0, and therefore, you will find that you can't fix all the rate constants and pre exponents arbitrarily, they have a relationship. If you are far away from equilibrium, you probably will throw away some of them. Therefore, you can specify the others, and the ones which are thrown away or neglected, you can say they can be calculated or they are not relevant here. So, both K1 and K minus 1 we will write in the standard form, K10 e power B1 e, K minus 10 e power B minus 1 e, that we know. We will also say that these are elementary reactions, therefore, B1 and B minus 1 are related. Okay. We write B1 as alpha F by RT, F is the Faraday constant, R is the universal gas constant, T is the temperature, alpha is what is known as charge transfer coefficient. So, here there is one electron transfer, sometimes you can write this as n electron transfer 2, 3 etc., in which case this is going to be multiplied by n, but right now by and large you are going to have single electron transfer reaction for this simple electron transfer reaction. Therefore, we will keep it as 1, and the reverse reaction will have 1 minus alpha. So, alpha will vary between 0 to 1, and if you do not know any specific value for that, if you do not have any reason to specify, we will just take it as half 0.5. Now, I want to find first steady state solution. Earlier we have seen this, right, we write the mass balance equation, charge balance equation, but that is with adsorbed intermediate. With no adsorbed intermediate, we just write the charge balance equation. We can find the steady state current. We will write the expression for current when potential is DC plus a small amount of AC, and then we will see if we can write it as del I by del E, which will become Faraday. Here we are going to go in similar path, but we will take some detour. When we come there, I will mention that. Right now, first we want to see how the current will vary when potential is varied. Earlier it was very straightforward, right. We will write it as I Faraday is F K1 Ca bulk, because we assume throughout the regime it is Ca bulk and it is a constant, minus K minus 1 Cb bulk, and this was K1 0 e power B1 e, this was K minus 1 0 e power B minus 1 e. If we say this is E and this is I, you can say when it is far away in the positive direction, K1 is large number, K minus 1 is negligible, therefore, it is going to look like an exponential curve. When it is large negative value, it is going to look like this. In between, both are important, so it is going to go through 0 and it will look somewhat like this. When we have mass transfer effect present here, or when mass transfer is also going to impact the result, this Ca at x equal to 0 and Cb at x equal to 0, they are dependent on the potential. So, we will have to account for this and get the result, and this is actually fairly straightforward, it is not that difficult. So, we apply potential and we realize A will be consumed or A will be produced depending on whether we apply positive or negative potential. We need to use Fick's law of diffusion to get the concentration at the surface, and the law that we use here is Fick's second law. For each species we write partial derivative dou Ca by dou T is diffusivity of A multiplied by dou square Ca by dou x square. I think people in chemical engineering would have seen, if you are in other field you can still, you might have seen this. Yeah. So, I am just expanding the current value here, I have not specified whether it is DC or AC yet. So, I will say K1 is written as K1 0 e power B1 e. Ca, we want to look at Ca at x equal to 0 and in general at any time t. If it is steady state, that means it is not time varying, E will become EdC and Ca at x equal to 0 will be some finite number. So, that means steady state condition we will take the derivative with respect to time as 0. We have two boundary conditions, one at x equal to 0, okay, how much A is consumed, that tells us how much current is produced. It also tells us how much B is produced. So, the rate of consumption of A, rate of production of B, they are going to be given by this flux dA dou C by dou x at x equal to 0 should be equal to dB dou C B by dou x at x equal to 0, except that the signs are opposite, right. If we say the amount of A that is coming here per second per unit area is 1 mole per square centimeter per second, then you can say amount of B coming here per that area, it is not going to be amount of B coming here, it is going to be going away, because A is decreasing in concentration, B is going to increase in concentration. So, you have sign change, and the equation here tells 1 mole of A consumed gives you 1 mole of E electron. So, that is given by IF, IF is the Faraday current divided by Faraday constant, and N here is the number of electrons as per the reaction, it is going to be 1 here. So, this is one boundary condition. At x equal to 0, we relate the Faraday current to the flux. Second boundary condition is EC. At x equal to delta, concentration of A is same as bulk, concentration of B is same as bulk. So, second boundary condition is given in a simple expression. First boundary condition basically relates the flux of A and B at the electrode surface to the Faraday current that is measured. Now, let us say the concentration of A at the surface under steady state condition, meaning time equal to infinity, I give E equal to EdC and then wait for long time. I can call it as CAS, similarly CBS, this is mainly for steady state condition. At steady state condition, this is going to go to 0. So, it is going to tell you this is time, it is time invariant, therefore, you can write this as within the boundary layer some integration constant, I am calling it as C1 plus C2 or A and B, does not matter. Within the boundary layer, concentration of both species A and B will vary linearly. Of course, slope value constants, they will be different, that is okay, but it is going to be linear function within the boundary layer. Okay. Given DC potential, can you estimate the concentration of A and B on the surface using these two boundary conditions? It is fairly lengthy, but I would like you to try that. Correct. Under steady state condition, at a given DC, I will write IFDC, Faraday DC current, is Faraday constant multiplied by the net rate, and I can write this as K1 DC, which means K1 at EDC CAS minus K minus 1 DC CBS. If you assume dA and dB are equal, it will become lot simpler to do, but it is not necessary. See, you have CA on the surface, no sorry, CA not on the surface, this is CA within the boundary layer, CA within boundary layer. So, it is a function of x, varies like this. CA on the surface is at x equal to 0. Okay. CB again varies as CB of x is going to be CB on the surface plus CB bulk minus CB surface by delta into x. So, I can tell you this is going to be the slope, this is going to be the constant, but we need to find the value here. CA on the surface is going to be given by, sorry, CA on the boundary layer is going to be given by CA on the surface plus CA bulk minus CA surface by delta multiplied by x, because at x equal to delta it is going to be CA bulk, at x equal to 0 it is going to be CA surface, and anywhere in between it is a linear interpolation between these two. This derivation. So, if I give you CA at x, can you find dCA by dx? dCA by dx is going to be actually a constant here. Therefore, dCA by dx at x equal to 0, you can also find that. Okay. So, you can find dCA by dx, dCB by dx, you can say dA multiplied by this must be equal to dB multiplied by this with a negative sign. Therefore, we can find a relationship between CAS and CBS, that is what I have given here, that is correct. See, we want to find both CBS and CAS. It is easy to find the relationship between CAS and CBS, and it is a linear relationship, you can get it and then substitute in the other condition, which is dA dou CA by dou x at x equal to 0, that is equal to IF by F. IF by F contains K1 DC, CAS, K minus 1 DC, CBS. We can write the CBS in terms of CAS. We can leave K1 DC and K2 DC as they are. That means, if you tell me the delta and you tell me the DC potential at a given RPM, given rotational speed, if I vary the DC potential, meaning at one time I will wait at this DC potential, wait for sufficient time, I want to know the current. Next, I want to move the DC potential to another value, I want to know the current. In order to do this, we need to know CA at the surface for that DC potential, CB at the surface at that DC potential, and that is what we are doing here. Once you know this, can you relate IF and the flux So, the first part of this equation tells us dA Ca bulk minus Ca surface by delta is going to be K1 dC Cas minus K minus 1 dC Cbs, and since we already know how Cas and Cbs are related. So, we can substitute for this in terms of Cas and other known values. Known values meaning we know the diffusivities, we know the bulk concentrations, and then rearrange to bring Ca on the left side, Cas on the left side. It is a linear equation, so pretty straightforward. So, please do that and check whether the expression that I have given here is correct or not. Normally, diffusivity will not vary that much. Operation of the cell will be at room temperature, maybe little bit higher, little bit lower. So, 20 degree, 30 degree, maybe 40 degree. Diffusivity will not vary that much. Okay. Delta can be varied to some level. If you estimate the delta, if you are keeping it stationary, of course, it is a large number. Otherwise, it will be maybe 100 micron, 50 micron, somewhere in that range, meaning you can vary it by one order of magnitude. K1 and K minus 1 on the other hand, you can really vary it a lot. So, potential can be varied, and with that the rate constant can be varied very much. The rotational speed can be varied to some level, and you will vary the boundary layer thickness. Diffusivity usually does not change that much. It will change with temperature, but not like 10 times higher, 10 times lower. You can also see whether it makes sense when you look at the expression. If I increase the potential, what happens to K1, what happens to K minus 1? K1 will become a large number, K minus 1 will become negligible. For simplicity, let us just imagine, or let us just say that dA equal to dB. Therefore, some of the terms will cancel out and become simpler. On the numerator, this will become negligible, this will become negligible. K1 is a large number, this is a constant, this is negligible. Therefore, it is going to become Ca, this dA and delta are constants, by K1 dC. When K1 is a large number, that means at large potential, concentration on the surface will tend towards 0, it will not go to 0. And likewise, if potential is left at 0 OCP, you should get the bulk concentration here. When potential is left at OCP, K1 and K minus 1 are related, and if we say that Ca bulk and Cb bulk are the same and diffusivities also are the same, then you would see that it will reduce to the similar expression.
So, numerator second term will come negative now, K minus 1 dC Cb bulk. If we are putting that Cbs value directly in that one, so we will get minus K minus 1 dC.
You are just imagining. Okay, do the calculation and then show me. I will give you an alternate suggestion. Let us say dA equal to dB, Ca bulk equal to Cb bulk. Let us say EDC is 0. Then what do you have in the denominator? K1 dC plus dA by delta plus K minus 1 dC, dA by dB is unity. K1 dC and K minus 1 dC are also same, but you will say retain it as K1 0 and K minus 1 0. On the numerator, you should get Ca bulk, because concentration on the surface must be equal to Ca bulk. That means you should be able to, Ca bulk and Cb bulk are same, you can take it out, dA by dB will become unity, you should have K1 plus K minus 1 plus dA by delta. See, it takes little time to do this, but it is worth your effort to do this. If it is really lengthy, take dA equal to dB and see whether you get an expression that you would get if you simplify this. So, if dA equal to dB, I would write then I am going to move further, saying that if you are given time, you might be able to complete it, and this expression hopefully is correct. Yes. Now that we have the expression for CAS, so whenever we vary DC potential, we know the K1 DC, K minus 1 DC, and then we can tell this is going to be CAS, this is going to be CBS, and we can write the Faraday current. I am not going to substitute it and give you a large expression. I will just say that if you are given a MATLAB or any other programming environment, you will be able to calculate it. Now, there is an equation which relates the rotational speed. This is angular rotational speed. Omega r here is the rotational speed of the electrode. Okay. This nu is the kinematic viscosity, and dA is of course diffusivity. Typically dA, dB, they are all in similar order, and this you can use it to estimate the boundary layer thickness. I don't expect you to memorize it. You can find it in any of the standard books. Lewis, there are few equations. One of the equations relates the angular speed to the boundary layer thickness. So I given an example. I think I made a mistake here. If I go to positive potential, A will decrease and B will increase. So I think this may be, but it will saturate. This will go towards 0, and the other species will go towards the CA bulk plus CB bulk maximum. If you go to very negative values, B is getting consumed and A is getting produced, therefore the concentration profile will just flip over. Once you know the concentration, you can also get the current values, and this is how it will look. So I have estimated it for different delta values. Obviously I have assumed some diffusivity, I have assumed some K10, alpha is probably as 0.5, I don't remember now. And if I change the boundary layer thickness by changing the rotational speed, I will get different current values. If the boundary layer thickness is 100 micron, that means it's slow rotation, then current will increase and then saturate. It's not 100% flat, but it's almost flat. If you look at the actual values, they will keep on increasing very, very slightly. If I go to higher RPM, I will get thinner boundary layer. Even higher RPM, even thinner boundary layer. So current originally, if there is no mass transfer limitation, it's going to become somewhat exponential here, and in between it's going to be like a curve that connects these two. You see, if you do the simulation while accounting for mass transfer effect, here mass transfer effect is not felt that much, it's not going to be very different here, but you never get to see the exponential curve. You would see it's saturating because of mass transfer effect. So people would call this regime as mass transfer limited regime, this regime as kinetic limited regime, and somewhere in between as mixed control regime, where both mass transfer and kinetic play a role. Here of course kinetics do play a role, but mass transfer is the dominant effect, and out here mass transfer does play a role, kinetic is the dominant effect. What it means is mass transfer limited current is going to be like this, kinetic current is going to be like this. If I assume that mass transfer is not slow, it is rapid, then the curve here that I get, and if I compare with the curve that I get including mass transfer effect, they will be more or less same. So if I change it here, for various deltas, somewhere here all the curves are more or less similar. I move little away, I see the difference, and even right here, if I do impedance spectroscopy, I will find the mass transfer effects are seen. Okay. So when both are significant, you call it as mixed control regime. In the potential dynamic polarization curve, you would get curves like this, and experimentally when you do, you will get curves like this. You do not get the exponential curve that you see for the ferroferry. If you want to do impedance calculation, it is going to be lengthy. So I will tell you that right now. Okay. So we will probably go through one more class, and if necessary little more than that, but I want to start with that. Okay. And this derivation follows the derivation given by Lassia. He has written a book. He has also given I think extensive introduction that is available in the web. Okay. There are different ways of doing this. One way is to use Laplace transform. Okay. Another way is to expand in Taylor series, truncate and proceed. That is what we are going to do here, because that is what we have been following so far. We will continue with that. We are going to say we give a potential EDC plus EAC, where EAC is given as EAC 0 sin omega t. So, there is a minor correction here, is EAC 0 sin omega t. Now, we know the standard process. We expand in Taylor series, truncate the higher order terms, and we say approximately, as long as EAC is small or EAC 0 is small, k 1 can be approximated as k 1 DC 1 plus B 1 EAC, k minus 1 can be approximated, and when we substitute here, concentration of A will also show fluctuation, concentration of B at the surface, within the boundary layer, everywhere it will show fluctuation. Only at the delta we are going to say it is fixed as concentration at the bulk. We do not know how it is going to fluctuate, we are going to derive that, but we are going to say that current can also be written as DC current plus an AC current. Because the EAC is small, it will have a steady current plus a fluctuation. That means, if I draw like this, if I apply only DC, current will be like this. At time t equal to 0, we are going to apply an AC. So, potential will look like this, potential will be like this E, and then it is going to be sinusoidal on top of DC. Current will look like this. Of course, it will take some time to stabilize, and right now do not worry about it, but we do know that it will actually oscillate and stabilize at a slightly different location, but very slightly. So, let us not worry about it. We will say it will oscillate, and after some time it will give what is called steady periodic motion. This is the current. I am going to say it has a DC part and an AC part, and I want to calculate the AC part, so that I can calculate admittance corresponding to the Faraday reaction, under the condition that mass transfer also plays a significant role. So, normally what we would have done is the following: we would have written k 1 as k 1 DC plus linear term, we would have written concentration of A as steady state plus concentration of A variation with respect to potential multiplied by EAC. We ignore the other Taylor series expansion terms, that is CA square, EAC square, EAC cube, etc. And likewise, we would have done that for k minus 1 and CB, but we are not going to do that way. And this area I should not have used, it is all right. Instead, we are going to consider CA, CB and potential 3 as independent variables, and it is possible to actually do that way. Okay. We can vary the concentration on the surface by changing the rotational speed. Let us say I go to some EDC. Okay. So, A is getting reacted, produces B, A is consumed, B is produced, and it depends on the boundary layer thickness. If I give 600 RPM, it will have certain thickness. If I give 700 RPM, it will have a different thickness. It is possible for us to vary the RPM and make it sinusoidal, meaning it will go from 600 to 700 to 500 at a particular speed. So, you can give a sinusoidal oscillation. The RPM will be something like this: 600 plus 100 sin omega t or sin 2 pi f t, where f may be 0.01. That means, every 100 second it will come to 600. So, it will increase, RPM will increase, go to 700, come down to 600, come to 500, come back to 600 and so on. Okay. That way what will happen is boundary layer thickness will also change, concentration on the surface will also change, although EDC is not changing or ED is not changing. Okay. Because this enables us to derive the expression, we are going to follow that method, where we say the current changes because the potential changes, current can change because the concentration on the surface changes, current can change because concentration of B on the surface changes. And in our case, next line we are going to say concentration of A and B on the surface changes because potential changes. But in general, I can account for change in current arising due to change in potential, change in concentration of A, change in concentration of B. So, that means I will write it as partial derivative dou I by dou E at constant CA/CB multiplied by del E, dou I by dou Ca constant potential and constant B multiplied by del Ca. That tells how much is the variation in Ca, and the third term tells how much is the variation in Cb.
Is there an assumption in assuming such a situation that the deltas are very small?
No, we do not assume delta is very small. You mean this delta, not the boundary layer thickness delta. Yes. Basically, this is also Taylor series expanded, chopped off. Okay, this del IF is basically we are expanding this in Taylor series not just around EDC, it is around EDC, CASS, CBSS, and you will have cross product terms. So, you will have terms like dou square I by dou E square, you will have terms like dou square I by dou E dou Ca, dou square I by dou Ca dou Cb. Because we are saying linear term, we are happily removing all these things and we are left with this term here. Yes, we are assuming that this del E, del Ca and del Cb are very small. Now, del E is very easy to write. We know it is a sinusoidal perturbation. So, we will write it as EAC0 sin omega t. Okay. Dou I by dou E, I take the expression for this, and when I fix concentration of A and concentration of B, only rate constant changes. Therefore, I take this, F is written here, derivative of k1 with respect to E gives me B1, derivative of k minus 1 with respect to potential gives me B minus 1, and this is left as it is, and del E is given as EAC. So, the first term is easy to do, second and third terms are also easy to do as far as the derivatives are concerned. Take this expression, take a derivative with respect to Ca, k1 of course is independent, Cb is independent, therefore, you are left with only f k1 dc. Take this expression at a fixed dc potential and fixed Ca, if I take derivative with respect to Cb, I will get minus f k minus 1 dc. So, we got everything except these two, and these two will take quite some time to do. So, we will stop here today.